Hello, everybody, and welcome to our first set of presentations for today. We have a session on Bayesian statistics now, and our first presenter is Yuval Berman, and he's here in Perth. And his presentation is called Revisiting the Age, the PFPR relationship using Bayesian analytics to uncover insights. Thank you very much.
Thank you. So my name is Yuval Berman. I'm a research assistant at the Malaria Atlas Project, and I'll talk about the age prevalence relationship. So I'll just go through some overall context, and then we'll talk about the pull and grab model that I've used and the fitting methods, and then we'll discuss the results and key findings. So just before I get started, the Malaria Atlas Project, we're a project that was founded in 2005 with the overall aim of improving situational awareness of malaria globally. So our main methods are around model-based geostatistics, and effectively, as a global community, we've gone from this level of understanding of malaria endemicity in 2004 to much more spatiotemporal detailed resolution in 2022. So if you're interested or want to learn any more, or use our publicly available data and just have a play around with it, you can check out the website. So just so we're on the same page, the Plasmodium falciparum parasite rate, it's a really common measure of malaria transmission intensity, and it's effectively defined as the proportion of the population that have malaria parasites in their blood at the time of testing, as an example there. So PFPR, or prevalence, is known to change with age due to many different factors. So when you're born, you have maternal immunity, which effectively keeps it down at about 0, and that maternal immunity wanes quite quickly. And when you combine that with the increasing exposure, PFPR rises quite quickly through the first 2 years, and then plateaus through the later childhood years, and then starts to decline as immunity due to previous infections and cumulative parasite load sort of kicks in. This has led to PFPR 2 to 10 being a really common sort of ubiquitous measure of malaria transmission, and you'll see it reported in world malaria reports and things like that, because it is thought to be the stable measure of malaria prevalence in a given area. And this relationship has been the status quo since 2007 when this paper was written, but a lot of things have changed since then. So we've had a scale up of interventions, including bed nets, antimalarials, and indoor residual spraying. There has been an increase in data, and there's also been a decrease in malaria prevalence overall. So the question then became, what can we learn about how the age PFPR dynamics have changed, and how can we best model them now? So to do that, we used the pull and grab model. Now, before I go any further, pull and grab are the name of the authors. There's not any mechanism or anything like that that it's describing. So the pull and grab model, it's a very simple 2-parameter ordinary differential equation mechanistic model where the 2 parameters are shown here. So the first one is the plateau, which is somewhat synonymous with that peak PFPR or PFPR 2 to 10. And as the example here is at 0.6, but we can vary that up and down. And the second parameter is what we call the slope parameter, or B, which effectively affects how quickly we tend towards that plateau. So it can be really low or quite high, and B equals 1.8 was what Dave Smith found in 2007. This is what our data looks like. So we have 50 different surveys from 2010 to 2022 across 21 different countries. And it's age month. So all the children there have their age recorded in months, as well as the level of malaria prevalence in the community measured as PFPR. And we can start seeing in some of the curves that sort of that canonical relationship come out for the first 5 years of life. So we used the pull and grab model, and the price that we set was for the slope parameter. We set a prior centered on 1.8, being that value that Dave Smith found in 2007. And we just used a normal distribution truncated at 0. And for the plateau parameter, we set a beta distribution with a shape parameter of 2 and a shape parameter of 5, which effectively meant that we were much more confident in there being lower endemicity, so 0 to 50% settings than anything above 50%. Then the prevalence is given by the plateau times 1 minus the exponential of the negative of the slope times the age, so this equation here, and that is the pull and grab model equation that we saw from a couple of slides ago, plotting out those curves. And then the number of positives is given by a binomial distribution. So this was fit for each of those 50 surveys independently. So I here in the notation is representing each individual survey. So we used MCMC methods to fit the two parameters of the pool and grab model independently. And you can see there the first 200 iterations for a particular survey. I actually took 10,000 iterations and also had quite a large burn-in, but just for illustration purposes, that sort of shows the red dot, how it picks different parameters and the fit that we found. And these are all the survey results plotted together. So you can see for some of them, like Liberia, it rises quite slowly to the plateau. And for Guinea, for example, it rises a bit quicker, even though their plateaus are similar. But on the most part, it fits reasonably well to each of the surveys. There is even some uncertainty intervals there, but it's a bit zoomed out, so they're quite difficult to see. In terms of convergence, we found that pretty much all the models have, or all surveys have converged, except for 6 on the plateau parameter. So the ones that we found an upper confidence interval of R hat to be above 1.01 for 6 surveys. We weren't too concerned about that. We thought that was reflected in large uncertainty intervals. And also we found that the pool and grab model as a whole struggled to fit as well in lower endemicity settings. So settings where the plateau was found to be below about 10%. And also the effective sample size was above 1,000 for all the parameters. In terms of the sensitivity analysis as well, the fits weren't super sensitive to the prior that we used. So here in the plots, you can see the plateau value and the slope value that was fitted with the black dot representing the original prior that we'd used, as well as some variations on those. So for a slope centered on 0.9 or a slope centered on 3, and also some different plateaus. So for the most part, they line up pretty well, or at least are within the uncertainty intervals. And the ones that were miles off, like these green dots up here, that was because the prior that we'd set there, so a beta with a shape parameter of 5 and 3, is much more physically unreasonable, where you effectively assigning a very low probability that there are low plateau values, which isn't exactly what we'd expect. So in terms of the results and biological interpretation of them, so one of our key findings was that the transmission intensity, which is measured via the slope, is linearly correlated to the peak BFBR. And we saw that this was particularly true in settings where P0 was greater than 0.1. So as I sort of mentioned, the pool and grab model doesn't do as well. You can see really large uncertainty intervals for the slope parameter for those lower endemicity settings. And I think that's because there's there's much more stochasticity that is driving the behavior. So this 2-parameter mechanistic model doesn't do as well in those settings where the transmission is much more stochastic. But for settings above that, we can see there's quite a strong positive correlation, which is intuitive. So when you say the transmission intensity should be related to the peak PFPR or the plateau that you reach, but that hasn't been shown before using this model. So Smith in 2007 wasn't able to show this relationship. We also find that the plateau wasn't reached by 2 years of age on average. So we saw that it was reached by age 3, which is later than was previously thought, but it's also really highly heterogeneous and quite variable between surveys. And it really starts calling into question that use of PFPR 2 to 10 as that ubiquitous measure of malaria transmission, and that age standardized value as maybe something that should be reconsidered, particularly because some of these surveys reached 90% of the plateau by about 1 year, and others took the whole 5 years to reach it. And as I've alluded to, the age PFPR relationship is quite context dependent. So the structure can vary according to geography, time, and in some separate work that we've done, even historical intervention coverage. So just to illustrate here, I've got the same fit, but this time I've split the surveys into the rural component and the urban component. So Mozambique, for example, it's the same year survey, but I've tagged it according to whether the tests were done in the rural setting or in the urban setting, and we can see different plateaus and different slopes would have been fit through that as well. So some of the next steps is to update the burden estimation framework in MAP with this new age standardization mechanism. But we also need to be able to address the question of what to do in settings where we don't have data, because it's so context dependent. We need to learn how to deal with settings where we don't have the data to age standardize any information that we do have. We can also explore further biological mechanisms and models describing the relationship, particularly at those low endemicities where I mentioned that the pool and grab model struggles, as well as adding new data sets and surveys into the framework when they do come in. Thank you.
Thanks very much, Eva. Our next speaker now is in Hobart, it's Zoe Coffa, and her presentation is Misadventured into Missing Data. There we go.
Okay, so my research was very much about proving that missing data in student assessment results is a missing data problem. It's not a simple solution, and I worked with Dr. Bronwyn Long for this research. So I'm going to start with a story. Really early on in my teaching career, I was faced with my very first misadventure form. So this student wasn't performing to full capacity on the day of the assessment, and I had to estimate their result. And what happened when I asked, how do I do this, was press this button here, and that will estimate the mark for you. If you don't like the mark, you can always change it. And that opened up a big statistical can of worms for me. I went looking into what happens with imputation in education. So policy-wise, not a lot is documented for internal assessment. There's a lot that's documented for external assessment. And because of this, we're ending up with a lot of different approaches across different schools, different states, within different faculties. The really important thing that they're missing is taking into account the missing data mechanisms. So if you're not familiar with missing data theory, we're talking about missing completely at random, where there's no particular student that is going to miss a particular test more than another student. There's missing at random, which means that potentially the level of mark is related to the next assessment being missed. And then there's not missing at random, which is very similar in that it's still related to that mark, but that mark is also missing itself. So we have unobserved data that actually dictates whether or not a student is more likely to miss an assessment. So there's no consistent approach, very ad hoc, and teachers also employ teacher judgment, which is where we all have in the back of our heads a character profile of every student, and that data is not captured in an assessment data set, but it's taken into account when we impute those results. So I went looking to try and find out why it was so inconsistent. And I came across a couple of studies that were meta-analyses of journals in education and psychology, and found out that a lot of these journals have missing data, and the handling of it is still very basic. They either delete the data or they impute with a single imputation. So at the research level, that's then informing the policies. So those policies are being written without much understanding of missing data. And so by the time we get to teachers, they're just working with whatever they've got. So they're not being told what to do, and they're just using the information they have at the time to make those judgments. So one thing that they are not capturing here is the idea of natural variation. And if you're going to assume that a student is going to perform exactly the same from one assessment to the next, you're kidding yourselves. Natural variation is captured in a lot of Bayesian approaches. And although for this particular study, I did a lot of stuff as an illustration because the complexity of the problem was going to take me outside the scope of my time that I had. So I focused on these couple of methods. So These methods all focus on predicting that posterior distribution of the missing values. So I went with multiple imputation and I looked at two different models. I looked at a Bayesian linear regression multiple imputation and one with classification and regression trees. Under MAR, those estimates should be unbiased if we've got enough of the important information in our data set. Then on the other hand, if you go a full Bayesian approach, they combine the imputation and analysis steps, and this is more computationally intensive, but we don't require that pooling that normally happens at the end of a multiple imputation. So this was my application. I wanted to try and see if there was a consistent, fair, and easy to understand approach to mark estimation. I specifically imitated a class where there would be legitimate misadventures, so students who would actually miss a task for a particular reason. And I also focused on very small class sizes. That's because most of my teaching has always been in very small schools. And when you have a tiny data set, I've had senior classes of 3 students, how do you estimate with such a small data set? So I constructed the mark books, so it's just columns of 4 assessments and their overall weighted final mark and their rank. And then I artificially removed the data at 1, 5, and 10% missingness. And then I compared that to my simulated results. So these were the different methods that I used, and for the sake of time, I'm just going to focus on those last 3. So MI norm is the Bayesian linear regression, and CART's the classification and regression tree. And then for the full Bayesian model, I used a Gibbs sampler. Now, using this, I'm assuming that the missing values come from a multivariate normal distribution so that it can just be added as an extra step. This is a big assumption and probably not the case. So this is really just an illustration of how it could be used. So results-wise, I'm focusing more on the missing at random because this is where we start to have issues. You can see in those bottom, see if you can see my cursor. Yes, good. Those bottom 3 results are not too dissimilar from the single imputation procedures, and they're incorporating that natural variation, which is much more realistic. You can see as the amount of missingness increases, all of the results tend to increase. So this is the average mean squared error of each of the estimates. And in general, these 3 were more robust to which task was being imputed. So I imputed for a topic test and I imputed for a trial high school certificate exam. When you got to NMAR and down to 9 students, things went a little bit crazy. Multiple imputation, the MSE just shot up. And this was because we had such a small data set to work with that the algorithm could not handle making those estimations. So it compensated by including increasing the variance. But in general, the Bayesian approach, even though there's an assumption of multivariate normal, it's not too bad, I thought. So the practical use of this, in general, multiple imputation is going to be difficult to interpret by teachers, but it might be easier to implement in a classroom setting. A Bayesian approach is going to be easier to interpret because you can interpret those credible intervals like single imputation. And you can collect data over time and update your results. So you've got to have this long-standing database. But the big issue is they need to have an understanding of Bayesian diagnostics. which is just a whole nother level. Whatever they choose, it needs to be a consistent approach. So my main limitations was that I couldn't get hold of a proper data set. I don't have information about what's currently being used because a lot of the companies are very unforthcoming with information. And this only covers really small proportions of missingness. I'd be interested in looking at when to impute and look at different tasks and topics and seeing how they relate to each other. So my key takeaways are that mark estimation is a missing data problem. We should be making missing data analysis part of this process. Single imputation doesn't account for natural variation. And we could incorporate these natural variation tasks, but there's some big challenges to overcome first. Whatever is chosen, it just needs to be the most consistent approach. Thank you.
Thanks very much, Zoe. Our next speaker is Hakim Jamaluddin. He's in Christchurch, and the title of his presentation is Gaussian Mixture Models via Histogram Valued Data. And it's over to you, Hakim.
Thank you. Thank you for having me here. Hi, I'm Hakim. I'm a PhD student working with Scott Sisson and Boris Baranja at the School of Math and Stats, UNSW Sydney. And we are from UNSW Data Science Hub. So now this talk is about modeling a mixture of distributions, and we want to do it cheaper. And how do we do it cheaper? So it is very much related to the research area itself, which is called symbolic data analysis. So symbolic data analysis allows you to transform big data into a small representation of that big data. Then you will just use that small data to do any statistical or machine learning algorithms. So this small representation of data can be in any form, including histograms. And today we're looking at how we could use that idea to reduce the computational cost for a mixture model. So I'll start with a motivation. Right, sorry. So, oh dear. Okay, the motivation. How do we analyze a mixture of some distributions? Of course, the answer is a mixture model. There are two challenges to a mixture model. First, the numerical issue. If we recall, when we do likelihood function, we often use log likelihood transformation because to avoid numerical issue. Unfortunately, in a mixture model, it still doesn't resolve the problem because of the very PDF function itself, because it includes the summation of the weighted PDFs. So where Elasticus in 1991, Dempster, via expectation maximization approach, has incorporated mixture missing data structure via auxiliary variables denoted as set. So the second challenge, which has been resolved hopefully until this work, is the computational complexity. Because imagine that we have large data, then we will have massive likelihood, and of course the computation is heavy. What if we can use that idea of symbolic data analysis by firstly transforming the big data into a small histogram that will make the likelihood small and the computation cheap? So some questions to address in this talk today is, while preserving all statistical properties of the original data. What does that mean by that is that we want to make inferences on the very original data level. So we want to make sure that we can preserve all the statistical properties. How do we aggregate the big data into a smaller representation? And then since we have aggregated the big data, we want to also know how to handle the auxiliary variables, because the auxiliary variable is the indicator variables for each of the observations of the original data. And then finally, for application, we want to derive some MCMC algorithms for statistical inference. So takes quite some time already. So we'll start with symbolic likelihood. Let's take a look at what symbolic data analysis is. First of all, right. In 2023, a paper published by my supervisors and one of the students allowed us to do statistical inference on the level of the original data, because back then, since 1989, by a professor in France, Didier, he managed to do it on the level of the smaller representation. So the idea is that you want to we want to transform the original data into symbolic data. We call histogram or smaller representation, and sometimes symbolic data in general. We want to transform that big data into smaller data, symbolic data, and the likelihood is given by the proportionality of the integration of the function that maps the original data to the symbolic data, multiplied with the likelihood of the classical data, and we integrate out the original data. For a univariate histogram, imagine we have some class boundaries. So the likelihood proportionality is as simple as you take the product of the PDFs at each of the class boundaries, and then you also take the product of the CDF of the bins to the power of the number of observations within each bin. So it can start from negative infinity to positive infinity. So that's the idea of a univariate histogram. So a question is, what if Y comes from a mixture of distributions? So this is when we have to deal with not only aggregating the data from big data into a smaller one, but also we want to deal with the auxiliary variables. So let's take a look at how we can do that. But before that, let's just recall what a mixture model is. So a mixture model is has a PDF of weighted PDF, and and it is weighted based on the component mixing weights, where lambda, denoted as lambda vector from lambda 1 up to lambda capital K, and the capital K denotes the number of components, where the lambdas should be between 0 and 1, and the sum should equal to 1. This is the likelihood, as I mentioned before. It is the product of the sum of the weighted PDFs. So if we log this, it doesn't solve the log the numerical issue. That is when we have to include the auxiliary variables. And once we've included the auxiliary variables, it becomes a product of the products. So I'm not going to talk further about this. I have 3 minutes left. But basically, this is the likelihood after given the auxiliary variables. So now let's take a look at how we can do that for a mixture model by incorporating the idea of symbolic data analysis. So just to recall again, we have these two terms for the univariate histogram likelihood. The first is the product of the PDF. The second is a product of CDF to the power of the individual count of observations within each bin. So now, after some derivation steps, we've got this for the likelihood of a mixture model via symbolic data analysis. So the first term corresponds to the first term here in green, and the second term corresponds to the second term from the original symbolic likelihood. Likelihood. So this likelihood is suitable for a random bin histogram where we observe some observations from the classical data on the class boundary. So which means that we observe that on the class boundary, so we have to include that PDF terms here. But what if we don't observe any on the class boundary? Then the first term disappears. But we make sure that the sum of the number of observations to be consistent as well. So then we derive some MCMC algorithms via Gibbs sampling and Metropolis Hastings. And then we'll have to address some questions via simulations. Firstly,
Excuse me, Hakeem, you've got 1 minute left, please. Thank you.
Thank you. What if we increase the number of observations, i.e. the sample size? Based on this, I have rescaled the y-axis. So this is a plot of the total computation time versus the sample size. When you increase the sample size from 100 to 10 million, we can see that the black line increases from 0.1 up to 1,000, meaning that it increases dramatically, if I can say. But for a green and blue line, they are for the symbolic GMMs, based on the green one being the random and the blue line being the fixed. It is more than random is more than fixed because we observe the classical data observation, so we have to include some additional term. And then, so we know that when we increase the number of observations, symbolic GMM does not really increase in terms of the total computation time. But classical, it does dramatically. So we know that it saves a lot of time, but is it accurate? I just want to say, okay, this is the final note here. I just want to say, with only 10 beans of a histogram, it can capture almost all the information from the original data. So that's very accurate and cheap. That's it. Thank you.
Thanks very much, Hakeem. Do we have any questions here in the room in Perth for the speakers today? And we have a couple on the Slack. No, okay, well, we move to the Slack. On the Slack, we have a question for Zoe. Oh, sorry. This is from Eben. Zoe, could you resort to simulations to generate differing scenarios from limited to rich data scenarios?
So the big issue with any sort of education data is how sensitive it is. It would take me a number of years to get permission to get data. I contacted a couple of well-known research, educational research bodies, and they couldn't provide me anything. They said, contact NESA. And then I said, okay, but NESA only has the external results. They don't have what I want, which is raw in-class data. And so, yeah, at the end of the day, the only thing I could do was to simulate that data.
Thank you very much. I think we have a question at the Hobart Hub.
Yes, I have a question for Zoe as well. I can see there's some justification for a missing not at random mechanism in the assumption that students who know they're going to perform poorly will not turn up to assessments. Did you look at any methods such as the delta adjustment method to account for this missing not at random mechanism?
Nope. Is the short answer. I looked at so many different imputation methods, and my scope of my study blew out very quickly. So the reining in of what I could look at in the time frame I had, because I did it over 12 months, was quite limited. So no, I haven't looked into it, and I'd be really interested in hearing your thoughts about how I could incorporate that. Thank you.
And Zoe, I have another question for you on the Slack. This is from Solomon. Did you consider the influence of priors and hyperpriors on the estimates?
I did consider it. Did I get to it? No. Again, it's a case of I had a big scope of things to look at, and it was just an illustration. The data itself was simulated from a combination of beta distributions and a normal distribution, which in itself, the multivariate normal assumption goes out the window. So it was really just, is this something that could be interpreted in the classroom or not?